Good morning, everyone. We are going to start in, maybe we'll wait a couple of seconds because not everybody has joined yet. Yeah, let's wait a few seconds and then we'll start. So today's subject is the SRA 5 again, but this time two new topics, HPC system software and application co-design. So let's go. So welcome to this 24 ETP4HPC webinar. I am Pascale, ETP4HPC's communication manager, and my colleague Maike is also here to help run the show. Hello, Maike. And yeah, quick word about our association for those who are not familiar with ETP4HPC. I'm sure there are not many of you, but so we are a non-profit association that promotes European research and innovation in high-performance computing. And we are a private member of the Euro HPC JU. That is, to put it simply, the organization in the European Commission that addresses HPC. And our role is to propose research priorities for Europe in the area of HPC. So that's exactly what we're going to talk about today, because though we are going to talk about some of the priorities that we identified. Before we delve into today's subject, a few practical information for you. So this webinar is recorded and you will receive the link tomorrow. This webinar is in listen-only mode, but you can see on the right-hand side of your screen the GoToWebinar control panel, and there you can ask questions or you can download handouts. So you can submit questions at any time during the presentation. We will answer them at the end, but I will share questions in the chat as they arrive so that you can all see them, and we'll handle them at the end. And also there is a handout section where you will find, today you will find there the SRA 5 in case you don't have it yet, and today's slides. So you can download the slides directly from the webinar today. And then I would like to introduce our speakers today. So we have invited Manolis, who is a principal staff research scientist at Force. Hello, Manolis. He will be our first speaker. And our second speaker will be Professor Dr. Erwin Laure. He's director of the Max Planck Computing and Data Facility, amongst other things. Hello, Erwin, glad to have you. And we'll also have several panelists because SRA 5 is not the work of one person or even a small group of persons. It's the work of a large community. So we have invited other experts who are involved in the topics we are discussing today. So Michael Mabs, I don't think he's here today because he had a last minute emergency, but I wanted to mention here because Michael, he's part of the ETP4HPC staff, and he's the coordinator, the Grand Master of our SRA 5. So hello to Michael, even though he's not here today. And then we have Andreas, Dr. Andreas Wierse from SICOS. Hello, Andreas, nice to have you. You're not a newcomer to our webinars. We've had you before. And we will also have Dr. Maria Perez from University. I don't speak Spanish. University Polytechnic of Madrid. I'm not sure that's the right way to say it. And hello, Maria. Nice to have you. Maria is also a board member of BDVA, and we interact a lot with her at ETP4HPC. And finally, I'm not sure Pascale was able to join yet, but she will join us later. Pascale Rossé-Laurent, she's a senior HPC architect at Atos. So now we've said hello to everyone, we can have a look at the agenda. So the introduction, that was me. Then Manolis will be our first speaker for 20 minutes. Then we will have 20 minutes for Erwin. And we will finish, if everything goes well, we will be ready for the Q&A session at 1:45 noon and with everyone here. So, Manolis, are you ready? Ready to share your slides?
Yes, please.
I will hand over to you. Yeah, that's fine.
Okay.
Excellent.
Okay, thank you
Floor is
for
yours.
organizing this. So thank you for organizing this event, and it gives us an opportunity to summarize what has been done within the SRA 5 team. And today's first presentation will be about a chapter that focuses on system software and management. There were three contributors and editors, Pascale, Maria, and myself, and I will be presenting highlights of this part of the SRA. The time frame for which we are concerned is 23 to 26, so it's not exactly long term, but it's I would say short to mid term on the topic of HPC at the exascale level. We had done the same work in the prior iteration of SRA, SRA 4. My very brief comment is that everything changes and everything stays the same. Computing continuum was a central concept within the SRA 4 iteration of the report, and it still is there. Still a great expectation. There are steps forward, and there are also new parameters to consider. I'm just highlighting concerns that I will be briefly commenting on. One is diversity of applications and an expanding computing scope. Environments where we have both simulation in the form of high performance computing, but also big data processing and also AI processing. There are complex hardware and software combinations. A big reason for that is to achieve efficiency, high rate of operations per energy unit consumed. And this requires tools that can support dynamic and flexible execution models. Tools remain a central part of this domain to assist in development, deployment, and optimization. And we do have this concern that we will be having multiple generations of hardware being in use concurrently. There are questions of interoperability, but also questions around how the runtime environments and applications can benefit from this infrastructure in place. The concern about carbon footprint was already picked up at SRA 4, and now it's even more pronounced. So being able not only to quantify the carbon footprint from infrastructure and use of infrastructure, but also to justify that the codes are actually getting benefits that are above this cost, So what is new or what is slightly different now? Well, the key drivers for this system software landscape remain, I think, the same: power efficiency, scalability, and also extreme heterogeneity. Complex combinations of software components and also hardware blocks. This brings forward new requirements or enhances prior requirements related to integration and delivery. This aspect of composing available components remain a very important part, and there is a process control aspect to that. And tools again remain paramount for us. This convergence or path towards convergence of simulation, big data, and AI on the same IT continuum remains a central aspect. And we see that this is achieved through more complex workflows, more advanced applications that can combine all these available technologies and make use of them in an environment where resource sharing needs to be a bit more flexible, and also remain efficient. The carbon footprint aspect, which leads to a discussion of sustainability. This was highlighted in our report for SRA 5. Whatever cost we assign to the carbon footprint, we need to see if it can be adequately counterbalanced by greater efficiency or larger scales of problems to be addressed on this complex infrastructure. There is a growing concern about trust and security. It's a way to provide the guarantees for actually making good use of infrastructure. And there is also some new concerns about open source, at least for the system software aspect. And these are around maintainability and compatibility across versions. So I'll try to give you some highlights of what the report has captured, and perhaps create some opportunities for you to ask questions or think about these issues yourselves. Let's start with the convergence scheme. So we do have compute-intensive workloads, which is the domain of classic HPC. So there, the primary concern is close to bare metal performance and very efficient use of expensive, high-end dedicated hardware. The usage model in this type of computation is that users are given time-based exclusive access to resources. But on the other hand, many of these users might also have needs around data processing or AI processing. This is mostly now done on cloud systems, where the availability of resources is slightly different than what HPC centers offer. Elastic availability is there a primary concern. So your consumption of resources can spike to a high level of consumption and then shrink down to a lower level of consumption. Fault tolerance and resilience remain important concerns there. And what is key there is that these are multi-tenant environments, in the sense that as we execute our workloads, we're actually sharing the infrastructure, whereas in the HPC world, we wait for our time slot and then we consume resources from the infrastructure. So in the cloud environment, we observe more of a self-service operating mode and rely on mostly pre-configured software stacks. This ability to reconfigure the resources and build what infrastructure is needed on top of the existing building blocks seems to be a primary concern now of growing importance, and it seems that they can drive the evolution of infrastructure, how infrastructure is planned, and likewise how it is operated. Again, I would highlight the aspects of elastic reconfiguration, which also pushes the boundary for the efficiency of schedulers and resource managers. Okay. New technologies around AI methods and AI optimized hardware, and also availability of data streams coming out of edge or IoT devices. They offer new potential for scientific workflows, and if these are tightly integrated in the workday of a user of the infrastructures, then this adds to the complexity of the infrastructure and the operations procedures. Understanding and modeling of data and workflows is quite challenging when we are in a multi-owner, multi-tenant infrastructure environment, and particularly focusing on data, not just computation, seems to be a disruptive change, in the sense that we need now to be more aware of where the data are available, and decide whether we move the data set, which is a common practice today, or rather if we just launch computation closer to the data. Given that now we have a broader span where our infrastructure reaches, then the security concerns become a bit more strict and quite complex to provide the trust relationships between the entities involved in the infrastructure. Particularly for resource management, I would say that one important aspect is that we don't have one global architecture for the entire environment that would combine the various types of processing that I mentioned before. Schedulers might be distributed, and scheduling decisions might involve some form of coordination. And there is also the concern of having a wide variety of resources, compute, storage, and communication. Integration of these resources is really what we are after at a good level of efficiency. Interoperability between HPC centers and perhaps cloud-style infrastructure seems to become a concern. Likewise, the efficient use of edge devices, particularly for access to data streams. So we need to consider this aspect of data movement, which is of course a long-standing concern between the layers, and to consider the quality of service that we can achieve under various alternative execution scenario, either moving data or computation to one layer or the other. The workflow seems to be the concept that binds together all these concepts. So having our work broken up into stages with some dependencies among them, and then have some sort of scheduling and orchestration that leads us to use the various layers of the infrastructure. If we want to see the infrastructure as a continuum, then I think this is a good abstraction to get started, at least from the point of view of the users of the infrastructure. Regarding efficiency, which is again a primary, remains a primary concern, there we have the added complexity of combining various infrastructure elements and various application execution environments. And there are some dimensions to this efficiency consideration. So already we are familiar with adequate or appropriate computing that might involve, for example, using reduced precision arithmetic to have a good enough result within a particular time frame, and application-specific hardware that allows us to have more operations per unit of time per watt. There is a challenge from the programmer's point of view to make good use of anything that is application-specific, but also there is a challenge that is growing in complexity from the side of the system operator and manager, how to combine the various different accelerators into a unified model. Unified programming models are of interest and concern for the application owners, but they are also a concern and primary action item for the side of the system operator, because all these resources are available in a dynamic and increasingly elastic infrastructure. So how can we make efficient use of expensive application-specific hardware and make it as accessible as possible to the application owners? This concept of in situ or in-transit processing seems to be quite promising. Basically, it's the idea that we could be operating on data that are generated by long-running simulations and use the data as they become available, or at a rate that is much faster than waiting for the completion of a simulation. From the big data part of the infrastructure, we do see approaches that are promising. This idea that you can place your computation at a convenient location as close to the data as possible. And we think that this is a promising direction and needs to be enhanced as much as possible. A variant of that, or even more challenging in terms of infrastructure, is how to handle streams of data that need to be considered for a long-running set of computations. And this brings us to the topic of data-aware system policy, where we have all these heterogeneous resources and large amounts of data at various formats, etc. Now, this makes it very difficult to have a view of locality. So we need tools that allow us to better understand when a certain volume of data is available, what processing is coming up for that, and perhaps adapt this execution and decisions on placements, etc., to automate the decision-making process on how to place data and computation in relation to each other. Again, energy concerns is what makes this an important question, and the energy concern is also combined with the carbon footprint, which is a sustainability concern. Again, a couple of words for the this aspect of sustainability and the carbon footprint. I think it makes us rethink life cycle requirements and the return of investment of what we deploy. So one question from which we can start is how to actually estimate the carbon footprint. I think any such estimate will need to rely on considering the entire life cycle, starting from the production and then the operational life of any component and how it is efficiently used by any interested user. It seems that there are some drivers for this concern to become even more important. So if we have a slowdown in how raw hardware speeds are evolving and the corresponding core performance, perhaps we have a financial incentive to keep our systems running for a longer period. I think this might be a concern for HPC centers at first. And having this with these assumptions in place, we might have in place several generations of hardware. So this provides new interoperability challenges so that we keep 2 or more generations of the hardware available and perhaps combine them in one long-running workflow. And again, from the operator's point of view, one starting point is the efficient and timely collection of metrics. Monitoring APIs that can handle large-scale infrastructures and lead to some model that drives our decisions on how to actually use different generations of infrastructure. In the SRA 5, there is a specific coverage of this sustainability concern, and I would encourage all attendees to take a look on that. And I'm just summarizing some key points from there. So we are doing an effort. We are working towards modular systems, and this makes it feasible to keep at least parts of these systems active for a longer period of time. This would be reducing waste and also allow for partial upgrades. I think this is the key benefit by doing modular designs. So one example is that we can keep the same servers, but perhaps upgrade our accelerators, gain performance while keep a substantial part of the hardware infrastructure unchanged. Increasing the system lifetime, well, also increases our the pressure for resilience and failover mechanisms to be in place so that users can experience fewer interruptions when they run their workflows on top of this infrastructure. And as I said before, having more heterogeneous platforms pushes the application owners to consider portability from yet another point of view, the point of view that, well, eventually they will need to be able to operate on a mixed hardware environment. And that is, again, a driver for the evolution of the software stack, at least from the point of view of applications.
5 minutes left.
Yeah, yes, thank you. I'll wrap up, I think. Regarding tools, I would highlight the shift towards hybrid HPC. So on-premises HPC augmented with cloud-based options. This again pushes our concerns about data-aware governance, where to place what parts, etc., and matching hardware resource capabilities with what the particular application-oriented environments have in mind. There are challenges coming from this coordination of application workflows and the management of resources and data. I would say that meta-OS and meta-orchestration approaches seem to be quite relevant, but there is quite a lot of complexity there. And the infrastructure operators are expected now to pay more attention on alignment of the various development tools and standards from the various types of infrastructure that they are expected to collaborate with. Improvements in scheduling algorithms and particularly hierarchical approaches, I think, are promising. And one practical aspect that seems to gain attention is that we need to have a standardized way to do information exchange between the components. The MIX is a promising standard in this direction. And if we go to more interactive usage of the infrastructure, for example, for decision-making support, then we need to consider more flexible usage modes for the combined infrastructure. And finally, I would like to highlight the importance of establishing an environment where we have trustworthy processing of sensitive data sets. This requires support from the operating system to provide essential security mechanisms, but also an infrastructure level design that allows us to make informed decisions about risk of exposure, etc. I'll close with this discussion of, or initial discussion of security risks. Even supercomputers are now more exposed to security risks. There are many more entry points to the resources if we take this workflow abstraction as the basic unit of work now. There are promising technologies around containers that could give us some guarantees about verified applications, or at least keeping track of provenance. On the other hand, we do need the flexibility, and the software stacks are not strictly built and maintained by one authority. They are not under the full control, for example, of the supercomputer system operator. We need to consider composability and evolution of this, and this makes the security guarantees even more complex to achieve. Just to highlight one complexity, there is no clear process to verify that a certain vulnerability has been identified and mitigated. So I think this is an area where we should expect more activity. And in the end, it comes down to sovereignty, I would say, protecting our infrastructure, and that includes both the technology and the data. There are some practical aspects. I'll just fly through the slides. I'll just say around open source, there are changes that need to be considered. All common practice and common, let's say, common sense approaches still are applicable, considering the licenses, the governance of open source projects, support models, probably commercial entities. All these need to be considered over an extended lifetime now for the systems. And I would say one crucial aspect is to have well-documented APIs that can simplify interoperability and exchangeability between software components if the need arises. So apologies for taking too much time, and please take the time to go through the SRA 5 document overall, and particularly our chapter. Thank you all for your attention, and looking forward to your questions and comments during our panel session.
Thank you, Manolis. So we will handle your questions at the end. So Erwin, your turn. Are you ready to share your screen?
I am ready if you give me the...
Yes.
Yes. Okay, first step. Second step. Let's see if I can get this into presentation mode.
That's
yes.
fine. That's fine. Thank you.
Good. Thank you. Yes, so welcome everybody also from my side. I'm going to talk a little bit about the application co-design, particularly, well, what are the opportunities and challenges that applications face in the quite changing environment that Manolis has nicely described, and not surprisingly, many of the topics that Manolis has alluded to are coming back here as well, as eventually we need to have an infrastructure that allows to run applications and solve scientific and industrial problems. And the chapter on application co-design was co-led by Andreas Wierse from SICOS, who is also here, and myself. So to start with, let me start with the opportunities. And it's not surprising that pushing the limits of computational power and computational capabilities now to the exascale and even further is really bringing a lot of breakthroughs in many scientific domains, starting from the fundamental sciences, understanding the nature of galaxies and stars, to particle physics. Climate weather and earth science is a very important use case. Understanding climate change, understanding the nature of the earth. In life sciences, we see lots of advances in structural biology, in personalized medicine. Energy is a big topic. How can we get sustainable in energy, renewable energy, fusion energy? How can we get more efficient in manufacturing? How can we get more and better materials? How can we deal with pandemics, which we always had on the list, and nobody thought that in 2020 this actually will become a challenge. And of course, we will have, or we see a lot of interest and uptake of machine learning and artificial intelligence applications also in the various scientific fields. Very often they are being used together with simulations, to steer simulations, to prune the search space simulations have, and so forth. But it's not only science that benefits enormously through the advances, it's also industry, although industry kind of has a more pragmatic view, so they're not trying necessarily to run at the extreme scale, right? They use in academic settings quite modest jobs with hundreds of thousands of cores, sometimes not even reaching petascale level. But they need to do this regularly and have a lot of different simulations to run. Run stochastic models, parameter studies, and so forth. So they are also a heavy user of HPC, but in a little different way than academics. But of course, they also profit and need advances in efficiency along the line. What is also kind of interesting to see is that, of course, it's large industries that use HPC, but there is also a lot of SMEs that require SMEs or are actually HPC that are actually specialized on HPC. And when it then comes to HPC usage, there is not really a big difference between large industry and SMEs. They solve the same problems. They need the kind of same computing power to do their work. Well, as we know, exascale computing is already here. We have since a couple of months the first exascale computer in the world in Oak Ridge National Lab, Frontier, which consists of AMD CPUs and GPUs. And I just want to, because I'm going back to that, think of the number that this is a total of over, or kind of 9 million cores that are working together on this computer, not talking about the power consumption, which is also enormous. In Europe, we have two what we call pre-exascale system. One is Lumi in Finland, which is the same architecture as Frontier, and the other one is Leonardo in Italy, which uses Intel and NVIDIA GPUs. But the landscape is actually broader than that. I'm just talking about the Euro HPC landscape. There's of course the national and institutional landscape that every country has, but on the European level, we have, apart from these two pre-Exascale systems in Finland and Italy, 5 so-called petascale systems that are smaller systems in the range of 5 to 10 petaflops in various countries. There is one more pre-Exascale system currently being deployed in Spain at BSC, and hopefully next year we will see the first European Exascale system in Jülich, which will be named Jupiter, and I think the procurement of that system is ongoing as we speak. And these systems, they are all quite heterogeneous. You've already seen a bit the details of Lumi and Leonardo, but also the others, they use different technologies, different setups, and it's very important that the applications are actually capable of exploiting that system so they are really useful for science and industry. But why do we need actually bigger and faster computers? Well, the big thing clearly is we want to get more realism, right, in whatever domain we are. And that very often means improving the numerical accuracy, meaning higher resolution that leads to larger system sizes, means you have more grid points in the CFD simulations, more particles, whatever. And I show you here how the transition from giga to tera to petascale has actually improved supernova simulations that first were only possible in 1D, then you did it in 2D, and now you can regularly do supernova simulations in 3D. The data that is being used and that needs to be analyzed is also increasing. We are building enormous new experiments. I have here an illustration of the square kilometer array that is being built, and that will likely produce over 600 petabytes of data per year that needs to be analyzed and processed. And not surprisingly, AI is starting to take significant computing resources. You all know about GPT. There is no precise numbers available, but likely this system was trained using several tens of thousands of GPUs, which basically is a kind of scale where we start to get into, well, perhaps half of frontier or so, and they used almost a year for doing that. So if AI is going beyond GPT, and which is doing now, so this is another major consumer of large-scale computing. I'll try to give you now some examples that show different aspects on how these systems are being used and what people want to achieve. And climate is clearly one of the leading examples. And they want to really do what is called a digital twin. So really have simulations, data, processes available that allows them to really simulate the Earth and then interactively see different scenarios, what impacts different actions have, and through that gain information and knowledge. And they did some back of an envelope exercise estimating how much compute power they need, and they also came up with a system kind of size of frontier with 20,000 GPUs and at least 20 megawatt of power that would be available. Going from the large scale climate simulations to the very small scale molecular dynamics simulations, here the question clearly is not so much to grow the systems, although you might have large systems with many ethons. The question is also how to increase the time scale. Going from nanoseconds to microseconds, for instance, and just having a microsecond simulation currently would need 10 exaflops. And you need then many of them if you want to study, for instance, like the example below, the effects of drugs and alcohols on ion channels in a nerve cell. So you really need way beyond zetaflop performance to do that, but the question is how you can actually parallelize that, because this is not really a standard domain decomposition. There you have limits. You need to get parallelization in time. Similar problems are with the material science, electronic structure theory, and here is really the complexity that is starting to grow enormously if you want to get better accuracy. So you start with the current workforce is density functional theory, which has n to the power of 3. If you want to go to the gold standard in quantum chemistry, you go to n to the power 6 to 7. And if you want to do exact diagonalization, then you are e to the power of n. So this complexity, raising complexity together with the aim to also simulate larger systems, clearly leads to the need going from peta to exascale. Fusion energy is another example. I have here one code gene that is developed by the Max Planck Institute for Plasma Physics that simulates the plasma in a fusion reactor. And this graph just shows what the enormous impact GPUs can have on the performance. So the lower bars is GPUs, but it also shows that we're now actually being dominated by overhead, by MPI communication, auxiliary routines, and so forth. So there is a challenge to go further in parallelization. And maybe a last example, which is a kind of, again, different beast, is urgent computing. Particularly when you have natural disasters, like here is a simulation of a volcano eruption, and you try to simulate where the eruption goes. You need not only large-scale compute power, but you also need to have that swiftly, which is another challenge to get the large-scale compute power quite immediately on your fingertips. So what are the challenges that we face? Well, it's the level of parallelism, right? I already mentioned that. So we have the order of 10 to the 9 floating point units, which are being deployed in the hierarchy of nodes, processor, different NUMA domains, and so forth. We have very heterogeneous hardware with CPUs, GPUs, different memories, high bandwidth memories, NVMEs, and so forth. Programming, particularly programming for portability, is an issue. We have standard tools that people are using like MPI and OpenMP, but there are proprietary tools, CUDA, particularly HIP1 API, but there's also abstractions that people use to get performance portability, like Cocos, Aracha, or Alpaca. We probably need novel numerical approaches. Composability is an issue. We need to go from single simulation to large-scale integrated workflows and think about the digital twin approach from the climate community. But we still have also a kind of a mismatch of technology and development cycles. So we have the codes carry a huge precious legacy, right? So there's a big tankers that cannot move quickly to new technologies. And we tried to actually cluster that a little bit to certain topics in the SRA 5. And we started with one challenge that is probably not only application specific, but goes across the whole HPC domain, and this is education and career paths. And I think we all need to work on that we get better educated people and that we attract people and maintain people, meaning providing them appropriate career paths. I think it's a non-technical issue, but it's one of the most important issues. When we come to the technical issues, it's basically the technical issues that provide currently main challenges to those applications and usage models that I've alluded to. We need lower latency and higher bandwidth for data access, particularly when it comes to artificial intelligence. We need workflows and ensembles, meaning how to couple the different simulations, how to allocate the resources, how to access the resources in a very dynamic way. We need to get overhead as much as possible out of the way, which mostly is memory bandwidth and communication latency. If we need to get to stronger scaling, like in molecular dynamics, where we need shorter time steps instead of larger systems. The storage and I/O of increasing data sizes is starting to be an issue. So we need more efficient systems there, and also Manolis has already alluded to in situ approaches, for instance. The long-term maintenance and portabilities of code is an issue, meaning how, particularly when it comes to these large-scale legacy codes, where do we find the Fortran programmers, right, that can still maintain them? What do we do with that? Are we rewriting them? Do we keep them? There's a lot of open questions. We need so-called dwarfs that allow to more easily experiment with different approaches, and energy efficiency will at some point in time clearly push us to alternative approaches, which can be quantum computing, neuromorphic computing, RNA computing. We don't know yet, but applications need to keep an eye on. And in Europe, we have a program which is called the European Centres of Excellence in High Performance Computing Applications, and they are developing these, or many of these applications, and trying to address those challenges. Centers of Excellence are pairing disciplinary expertise in the various domains with HPC expertise. HPC expertise from the programming side of view, but also from the hardware point of view. And this program has actually started back in 2015 with the first wave of Centers of Excellence being funded, and since then we had 4 rounds of funding of Centers of Excellence. In 23, Euro HPC has taken over, and another round of funding will probably be launched next year. And these Centers of Excellence, they try to cover a large space in the different domains that reaches from Earth and space systems to fundamental physics, material science, engineering and tools, and biology and life sciences. So there's various of these projects that deal with those issues, and I've shown you some examples already. And if you want to learn more what these Centers of Excellence are doing and which impact they have, there is a brochure that has been issued, and you can find this under this link given here. So, to summarize, we now have exascale computing, which is good, which enables exascale simulations, but more importantly, enables routine petaflop simulations. But it also has to be said, it's on GPU accelerated HPC clusters, right? All those systems, they are heavily GPU dependent. And that's one of the issues we are facing in HPC. HPC is not a market that drives technology, at least not driving technology to a large extent. So the commercial drivers, particularly for hardware development, they come at the moment from machine learning and artificial intelligence. And that means that we see these special execution units like the TensorFlows, more efficiency in lower precision and so forth. And HPC applications have to adapt and have to see how they can follow this hardware development, because just staying with CPUs and hoping that they will be faster, this is not going to happen. we see new approaches that are being enabled now by having larger systems available, like multi-physics and multi-scale problems. But of course, they need even more compute power, and they need probably eventually a combination of simulations together with AI technology and novel technology to come, perhaps quantum computing. And the third big challenge is really the sustainable application development. There is a huge legacy in the flagship codes, which very often are Fortran, which very often are CPU only. So there's a lot of work that needs to be done. And unfortunately, there is no low-hanging fruit. So we really need to have these multidisciplinary efforts like we have them in the Centers of Excellence, where you have the domain science, numerical people that develop algorithms, getting better software engineering in there, and the corresponding HPC technology. Then we probably can make sure that the investment that Europe is making at the moment, which is great, into lots of compute power and hardware, is actually going to lead to new scientific discoveries. Thank you very much.
Thank you, Erwin. So let me. So do you see my screen now? Yeah. Oh, but we are back at the beginning. What have I done? Okay, so if we have a first question. Sorry, I'm trying to display the right thing. Now, that's better. Okay, so yeah, I have a first question. Sorry, I wanted to share it in the I'm trying to copy it into the chat. Yeah. So we have a first question from Alexandros Kontinis, a question to both of you, to Manolis and Erwin, and to the other panelists. Welcome on board. You presented trends and challenges around hybrid HPC, cloud resources as augmentation to on-premises HPC resources, and challenges around heterogeneity of infrastructure as a whole. Do you see a significant shift to containerizing HPC applications to be more agnostic to the infrastructure and to enable the more complex workflows mentioned? So the question is in the chat for everybody to see. Okay.
So maybe let me start from an application
point. So who
point.
takes it? Erwin? Okay.
Yeah, let me start from an application point of view. I've alluded to this already a little bit. There is clearly a big issue in performance portability, and containerization could be one approach. What people currently do more is to have performance portability abstraction layers. I mentioned Raja and Cocos, for instance, and they are starting to be used more frequently. That's the first step. The second step is then really going to use containers, which we also see, but this is at the moment more or less limited to those applications that really need to run across the whole spectrum from cloud to various supercomputers. Applications that only run on supercomputers at the moment do not use this yet, but I believe containerization is a technology, particularly as the overhead is getting less and less. We're seeing very efficient container technologies these days that I guess for the future will have a significant impact.
Anything to add, Manolis, or the other panelists? I mean, Andreas, Maria, Pascale, you have not talked until, you have not spoken until now. So really, I mean, if you have anything to add, feel free to step in.
I agree with the answer of Erwin. What is important is to have the performance, that keep the performance. The containerization is important, but what we need to have in mind is that we need to have performance of hardware that is keep in application, and for that I think that much more the application will be developed with libraries that will be optimal for some type of hardware, and I think it's a way to have the performance, to keep the performance. And the second part is that application is, as we say, involved with workflow, and probably we will have some part of the workflow that will be optimized for some type of hardware. So I think container will be a solution to be able to transfer an application from one hardware to another, but we need to progress on the way to optimize some part of the application on some part of hardware.
I was wondering when I heard it, and Erwin said the overhead of this containerization is getting less and less, which means, however, that the hardware dependency between the code and the environment it runs on will still be important. So containers will come, but well, to put it to an extreme, you will be not able to have a container run on a classic HPC system and then take the same container and put it onto a quantum computer. So I guess there will be a big impact on the workflow level. If you have workflows and you can work with different containers, I think it's kind of an abstraction layer, but it will not solve anything around the portability problem, I think.
Okay.
Well, I would like to add a short comment about what was said already. I think containers are part of the solution. It's not the full solution, as the prior speaker said. I would say from the HPC point of view, the performance portability it's a much deeper concern, and Erwin kind of hinted at other aspects, not outside of the way we package the software stack. I'll just highlight two problems in the current technology. One is around device interfaces. Let's say we want to expose high-speed network resources to our containers. It can be done. It's not standardized. There are multiple container engines available. There is Singularity, there is Podman, there are slight differences, and there is activity around these technologies. I think that's important. I hinted also to a trust or security concern, tracking the provenance of the software stack. So if I have one large unit that contains all of my software dependencies, etc., if it carries, for example, a set of signatures, I can have some assurance about the source, the origin of the code. So container technology helps there, although it was not designed for that aspect. But I would say for the workflow aspect on heterogeneous platforms, I think we have a long way to go. You can see it as a half empty or a half full cup at this point. I would say there is significant work being done in containers that might make them a bit more, let's say, performant, and that would encourage people to explore how they can be used in more complex deployments. So it's kind of a chicken and egg. So they are not there is some overhead. It's not prohibitive for deployment, but there are little things, for example, the device interfaces that I think have kept the adoption lower than I would have expected at this point in time. I don't know if this makes sense for the person that asked the question.
Okay, thank you very much. So a question from Fabrizio Maguliani. What may be the impact of the European Chips Act on the current and future environment? I guess he does mean chips, not CHPS. Who wants to answer this one? That's a political one.
I think that here, Maria from my side. So I think that all the advances that have been made in semiconductor technologies will have a large impact on the future environments, especially on aspects related to energy efficiency, increase of performance, and so on. So I see a clear relation between these advances in semiconductor technologies and the future environments.
Thank you. Anybody wants to add anything?
It's also a question of sovereignty. So I think it's important to follow the activity of the Chip Act and to be able to prepare software stack and application to the new technologies that will be funded in this Chip Act.
Thank you.
So from an application point of view, of course, it's great if we have more choices on the processor and chip level, and if there is European competitors to the others. But as already was said, applications need to have the full stack. It's not enough to just have the chip technology, right? There needs to be particularly the system software, the compilers, the libraries, and everything that the application can run on. And of course, applications will not run on one specific technology. They need to run on all the technology that is available worldwide. Science is international, right? So we need to be able to run on the European, US, Japanese, whatever systems.
Thank you. So we're running a little bit behind schedule, but I would like to take the last question. We have a question from Herbert Owen. The latest COE call states research activities on the basis of use cases are not within the scope of the action, and use cases should be limited to test runs required for development purposes, such as regression tests. This seems to exclude production runs at Exascale. Do you think this is so? Now, who has insights about this?
Maybe I can take that.
Okay, Erwin.
Let me start off that I was not particularly happy how the latest COE call was phrased and certain aspects of that call.
We're between us. We want this one go further.
This is one of them, one of these aspects. There are other aspects that we can have a chat over beer where I'm unhappy with. Of course, there is always the tensions between development and doing real science. And clearly, if we fund HPC development projects, application development projects, this should not be misused to co-fund, get an alternative funding into the proper science that people want to do. Having said that, you cannot do application development without running real production cases, because only when you run at a large scale and long term, you uncover the problems. So I find this current policy of Euro HPC a bit problematic. I do understand where it comes from, but yeah, let's work together to make them change their mind.
Does anybody want to add anything to this or no? Okay. So I think we will stop for today. Does any of you, especially the panelists, if you have anything to add before we close the webinar? I mean, it's open to you. Pascale, Andreas, Maria? No, nothing to add. Erwin, Manolis? No? Okay, well, I just want to thank you very much for being here today. The next webinar will be on the 23rd of June, and it will be indirectly related to the SRA 5. We had a very good session, a live session at the Euro HPC Summit, and it was not recorded, unfortunately, so we decided to do it as a webinar. We'll do it in two parts. So first part will be on the 23rd of June. You will receive an invitation. We send invitations to all our webinar attendees. So a big thank you to Manolis and Erwin, a big thank you to our panelists, Andreas, Maria, and Pascale, and hope to talk to you all in June. And we'll probably see each other at ISC in between. Bye-bye, and thank you very much.
Thank you.
Bye.
Bye-bye.
Bye, thank you.